Hello everyone, today I'm going to deliver a lecture on design of section for flexure. The whole time, what is the difference between design and analysis? Design means we have to find out the section which is breadth, depth and the required reinforcement. And if we analyze the section, then what will be find out that we will find out for analyze stress, deflection, rotation, dead load, live load, like this. So in this part I will show the design, that means section depth, breadth and reinforcement required, area of reinforcement. Okay, so let's see. First of all, I will try to deliver a lecture on preliminary design and give some math example of preliminary design, and I will introduce the current, then 3 will the elastic design for general concept, and fourth one elastic design, number of no number of tendon in concrete or final design you can see, and the math example of final design, and then elastic design remarks of remarks on allowing tension, and elastic design remarks on allowing and considering tension in concrete, and math example of redesign of beam section, and allowing and considering the tension, and elastic design composite section, and math example of the composite section, and ultimate design, and with math example and shape of the concrete section, like I section of I section, T section, box section of the girder, and arrangement of the steel, prestressing steels. Okay, so let's start the preliminary design. So before going to the preliminary design, I'm just saying here is a the all are taking the reference. We can see the design of prestressed concrete structure, third edition TY Lin. Okay, these books I have been taken from all the here, and okay, so here we will see design of the section for flexure. We can see area of concrete, area of steel, prestressed steel. So we can see there are the two type of design, which is preliminary design, there is a final design. I have been seeing this is the preliminary design, and final design we have been seeing here. So here is the preliminary design. So in this way, how we get the preliminary design? So you can see moment into force into perpendicular distance. You can see force is which is compression or tension force, and moment arm. This is the moment arm. And how will get the tension? It's a moment divided by moment arm, and force how will get mt, which is m, and divided by moment arm, and force mt divided by moment arm. It is taken from 65% of 65% of total weight. And then now area of prestressed steel, FPS, we can see force into stress into area, we know this is the area into stress. And how we'll get this? This is the force initial minus force steel divided by force initial divided by steel. You can see for after cutting this, and we will find this. And we know the S. If we rearrange them, then we can found the area of steel, which is force divided by stress. So we can use the for prestressed steel. You can see the force as we multiply with distance, that will be m, and we've been seeing the 65% of is. Okay, so now area of concrete, how we calculate this? Area of concrete, we know equal to area into force into stress. So stress will be 50% of advance, as we know 85% we've been taken, but in this case we have been seeing 50%. So if we calculate m, multiply taken into moment, so we will get the 65%. We will be adding this. So average stress can be assumed to be 50% of the maximum allowable stress, which is given in this page. So we've been seeing I section of the I section of the beam. This is the H, and this is the 50% of stress of concrete. Is this is here, and the compression force is taken from 65% of from bottom. This is stress. This is tension stress. Okay. So mg, which is the girder moment, is self weight of the moment. Mt is the total moment. If we know the girder moment divided by total moment less than 2, then we can use the I section. If the girder moment and the total moment is greater than 2, then we will use the T section. Okay, let's go to this book and see at a glance what happenings. So we just seen here the preliminary design. So lever in the internal couple is could vary from 30 to 85%. So overall the height is average about 65%. That's why I have been taking 65%. 65% of the total is in this year. So in this we can calculate the force. We've been seen already seen this and this formula also and this formula also. Now we've been seeing here the preliminary design of the beam section. We've been seeing that this is the 50% of H for concrete. I have been shown here this diagram. And 62 the coefficient is the here is the above the procedures only approximate met the coefficient of 65% and 50% of the 50%. Okay, so let's see an example how we calculate. Okay, so you can see the make a preliminary design for the section of the prestressed concrete beam to resist the total moment which is given 345, and the overall depth is section is given as this, and the coefficient of the pressure of steel is given also, and allow the stress for concrete under the making load is given this stress. Okay, so given that as we've been seeing the total moment and H is given a stress of prestress steel, and stress is concrete, and girder moment is given here. Okay, so the section we've been seeing here. So preliminary design, we know the girder moment divided by total moment we've been from 0.4 which is greater than 0.2. So we can use that T beam. So we can use we should use T beam as we've been seeing here and previously been seen here. So that's why we will use T beam. So let's see the force we will using as usually this formula and founding this value, and A equal to the force into stress, or if we multiply with depth or age, then force into distance, it will be moment, and similarly we will use the age, so which is 65% of age, and it will be like this, and found the area. The concrete area will be in the same as force into stress as we have been use. We know the force equal to area into stress, and it will be we are taking this converting here and found in this value. Okay, so now we can see the now we are now we have been seen here the girder moment divided by total moment, which is greater than 0.4. So T section would be used. Now we can see the detailing of the section as we have been found area of concrete is this. So how we will calculate this? This is after finding this, we are just drawing this T section, as we know that T section will be used. Then we are using T section. But we have been found the area of concrete as we have been seen here 1.2 10 to the power 5. So in firstly we have been shown the 30 300 is given the wire flange width, and 720 we have been seeing this is the 720 we have been taking here, and now we calculate x1 and x2. What is the x1? This is the x1 and this is the x2, but we have been taking manual trial by manual trial. So provided we have been seeing this, so if we calculate here and trial, then we will finally we been found this value. Okay, so I hope that the preliminary design has in that. Now we can see another. Okay, so sorry, there is another example. They make the preliminary design for the beam section is given, the total moment is given here, and girder moment is given here, H and F steel stress and concrete stress given here. All the data is given here. We are training girder moment divided by total moment. We will see which is less than 2. So we will use the I section. So we know the force equal to mt divided by total moment divided by girder moment and 0.5 into h, and found this value. And area of steel, we've been know the force into stress and found this value. And area of concrete, we've been used the area into stress and 0.5% of FMC, and found this value. So area we've been found of concrete area, we've been found this, and steel area we've been found this. So now we'll divide the concrete, I will get this. So we know the 100 into 70 and 100 into 10 into 10, and it will be 1500 square. It is approximately been provided. So these are the approximately, but it will be taken from more and more trial, as we have been seen the previously. I will get this. This is the trial processes. Okay. So moment of inertia we can calculate also this in this way here. Okay. So now we can see the current. Here is the current. What is the current? Current is a section in the region which is compressive point. Load may be applied without providing any tension stress on the section. So it means if we providing in a load in here in compression, then in this way in this section we will not providing any kind of tension reinforcement. So you can see here L by 3, L by 3, and L by 3, L by 3, all the section will be here. C when C is out of current, then the diagram will be like this. When C is inner the current, then diagram will be like this. What is the C? C is nothing but C is the compression load. It is the depend of the stress diagram. So you can see the stress diagram here. The compression block is A and T is here. So you can see T is CT, which is top C and bottom C, and CGS of concrete. We see here a CT of top C and bottom C is here, and CGS is here. So if we calculate KT, this is, remember, we will R square divided by CB when we calculate the KT. On the other hand, if we calculate the CB, KB, which is bottom, then it will be R square into CT, which is C top. What is R? R is nothing but radius of gyration, which is root over I by A, and CT, which is top CGS to top distance, which is Y minus H minus Y bar, and CB equal to bottom distance Y into Y bar. So let's see the current I've been taken from mechanics of solid. This is the combined stress and bending stress at footing. It is taken here. We've been seeing the axial load is here. If axial load is applied in eccentrically like this way, so it will divide Ex into Ey. So how we will calculate the stress eccentrically? We've been seeing stress eccentrically axial plus bending stress, which is minus P by A minus Fy by Ix into minus Ay by Is. In this way we will found minus B by 2 and minus B by 2. That means in this point, and found in this way, as we know, this it will be 0, as there is tension is positive, but we want to negative. That's why we are taking here. So in this way, after the calculating here all this, putting this value, we have been found Ui into 6 divided by Bu is 6 divided by 2, and we have been found less than 1. So we have been seeing this is the 6 divided by 2. That means if we calculate the 6 divided by 2 and 6 divided by, that will be H by 3, and this will be H by 3. That's why I have been shown here, and it will be L by 3, L by 3, and L by 3. 6 divided by 2 and 6 divided by 2, it will be H by 3 or L by 3. Okay, so let's see the determine the current of the solid circular cross section. If the cross section is like this, the load is applied in eccentrically distance from R, then we have been found this value. As we know, the axial load and bending stress, force into area into My by I enter 0, and putting the force into area pi r square, as this is the circular. And how we calculate the I? This is the I. We know the circular. That's why pi d to the power 4 into 64, and what is the d is the 2r, that's why pi by 4 into r to the power 4. We've been using this formula, and after this formula we have been found r equal to it will be r by 4. That means this distance are equal to radius divided by 4. Okay, okay, I think you have been getting the some knowledge on current. This is the current. So let's it is completed. So let's see the elastic design general concept and elastic design no tension in concrete or final design. Okay. Sorry, there is another theory. There is another theory of current. We can see here. C is below the current. We can, if the C is below the current, this is the current top and bottom. C is below, then it will be diagram will be like this. And number 2 phenomena. This is 1. This is 2. C at bottom current. So this is the bottom current seen. Then the stress diagram will be like this. When C within the current, so C is within the current, then the diagram will be like this. And number 4 phenomena, which is C at CGS, that means this, in this way the stress diagram will be like this. And consequently, when C at the top current, this is the top current, we can see KT, then the diagram will be like this. And it will be vice versa when the top current in the bottom, this. So it will be vice versa of the diagram. So C above the top, we can see above the top, that will be diagram will be shown in like this. Okay. So so let's see an elastic design, a general design concept. So let's see. I'm just a general design concept where. Okay, this is the general design concept. As we know that there is a prevailing compression of the design of prestressed concrete section much more complete with that with the reinforcement one. We can see here. Sorry, my you can see here the load is 2-point load. We can see the 2-point load is even here. The variable prestressed concrete beam we can see, and the external moment is 0. There is a 0, and C in T and C is given, and the smallest external moment is small. This is the small as the eccentric load. The largest external moment is large as the eccentricity is large. And the constant ZE is a reinforcement concrete. We can see in the external moment is ZET and C equal 0, and external moment and small external moment small T and C have been in here. The larger external moment have been seen here. So this is the general concept as we've been seen. The C below bottom current and top current, as we've been seen. This is the general concept. So these are the general concept. Okay. So it is completed. Now we'll see the elastic design node tendon in concrete or final design, we can see, and math example. Okay. So let's see. This is the elastic design on no tension in concrete. In this section we will discuss the final flexural design. This is the final flexural design section based on the elastic theory and allowing no tension in the concrete, both transformation and under the working load. Okay, so you can see this is the stress distribution of no tension in concrete, smaller ratio divided by girder, moment of girder divided by moment of total moment. The section property to have been seen here, and just after the transformation C, bottom current we have been seen here, and under the working load K is given here. Okay, so so let's see an example. Then it will be this is the final design as we've been seen. The stage we've been seen. First stage, the look at the CGS by CGS, which is E by this formula, FB into E minus K bottom current minus moment equal to girder moment. So in this way you can calculate it is eccentricity E, this formula. KB is a bottom current, so R square divided by CT, as we have been seen here. R is their moment radius of gyration whatever R is C, and in this ratio you can find this value. And step 2 is use the location of the CGS calculating F and FC, and the total moment will be used this formula, and force will be found this way. And kt, what will be kt? Kt will be asked to cb, and the f not equal to will be this here, and remember f not equal to greater than f. And number 3, the compute the requirement concrete area. This is the final design, we can say. The concrete area at bottom we've been seeing f not equal to this formula, and s into top fiber stress is take and found this way. So we'll found the SC bottom and SC top. So we'll use which one is greater. So let's see the example, it will be clear for you. So we've been seeing for the preliminary design section obtained in example 6.2, and previously you've been seen here 6.2. This is the 6.2, so you've been seen here, so I'm not showing again. Make the final design allowing fb is given here and f naught is given here, and other value is where mt, m girder total moment, and girder moment ft, fiber top fiber stress, and steel fiber stress is given here, and force is given here, and preliminary design section same as figure given. This is the figure given from taken from preliminary section design. Okay, so given not allowing tension have been seen here, all the data is given here. Now from example 6.2 we've been found this data we've been found example 6.2. Now step 1, look at the CGSOP as we've been using this formula, just using here. So what will be value of f? So we've been taking 8.3 10 to the 5. We've been taking it is taken for example 6.2. This is the example 6.2. We've been used the f. Remember there is no we will not using this f, other than we've been used this formula, this data. And in this way we will using the eccentricity which is found in here, and we've been seen the r is taken from this using this formula, and k current bottom is taken this formula, and k top and k bottom as symmetric, as we've been seeing the symmetric, that's why the top bottom and bottom current will be same as, and ct we've been seeing y minus h minus yt is found 120, and cb is the same as. Now we'll do the step to use the location of the CGS, which is using the force, and using this formula found this value, and f naught initially have been found 2.9, and f naught will been seen the greater than f, which is okay. So compute the requirement area of SE as bottom we've been found this below force, and at top using this formula and found this below. So we've been seen the top is greater, sorry, the bottom is greater, that's why we will using the bottom area. So we've been seeing SE bottom is greater than the top, so required is bottom. We will use the always we will use the bigger value. So increase the section increment and redesign. Okay. So I have that this is just, now we'll see the elastic design remarks of allowing tension. So remarks on allowing tension. So let's see from where, from this book. Okay, elastic design remarks on the allowing tension. In the preceding section we discussed the design of prestressed concrete section allowing no tension stress. So you can see here the stress transformation we've been used this here. The bigger arm of steel when the allowing tension in concrete, this is the bigger arm. So bigger arm we've been seeing here tension, and CNT is the bigger arm. And we've been seeing the relative significance tension in concrete. We've been seeing here the tension is T, and T is here the stress block with the tension of concrete and larger point of T. Okay, these are the in that. So now we'll see the elastic design remarks of allowing and considering tension in concrete and math example. Okay, so these are the allowing at considering tension. We can see in this method we should use the within the understanding that the stress calculation are not only exact correct if the tension stress except the cracking stress for the concrete, and it will be convenient method for yielding result and compared to the those. Okay, we've been seen allowing and considering tension in concrete. The proposed section, this is the proposed section, and stress distribution at transformation, this is the tension, and this is the compression, and this is the fiber. And stress distribution under the working load, we've been seeing this is the tension, this is the compression. Okay, so method we can use this following this formula. Now we'll see the explanation. We can see the elastic here is a elastic design allowing concrete and tension. Okay, I'm just taking the bracket is here. So this method should be used in the understanding the stress, calculating exactly if the tension is exact. I'm just saying here. So in the real field we will use the allowing tension. So we've been seeing the properties of the section, we've been seeing CGS, this is the value of this is the free stress steel. So between free stress steel and CGS it will be E, and we'll calculate the K bottom and E1 and E2, and this is the C. The C in the upper portion is E1 and below portion is C2. So stress distribution we've been seen is T, and stress distribution under the working load is here. So at first the step is location of E, and we'll using E equal to C1 E1 E2 plus KB, as we've been seen here. E1 E2 plus KB, this will be total E, and I will calculate E1 using this formula, U2 is using formula, and KB is using formula. Step 2, F final F and initial F. So F is allowing in this way, and A is the preliminary design. This is the preliminary design, and F initial is found this way. And step 3, this is the final outcome. We've been found concrete bottom and concrete top. So concrete bottom we've been using this formula, and concrete top we've been using this formula. So let's see an example. So redesign the beam section is example. We've been seen the 6.3 as the previously we've been seen. We have seen this the 6.3. So our recommendation was the increase section and redesign. So now we'll see the redesign. We'll do the redesign, allowing and considering tension in concrete, and data is given here, and others value are given here. So I'm just keeping here the allowing tension. We've been found this for preliminary design 6.1 we've been found here, and we've been in T section Y bar, then CBTB, it is the very important. So now E1 we've been use this formula, and E2 using this formula, and totally will be E1 plus E2 into KB, as we've been seen in this figure. The totally will be the summation of the 3. That's why we've been summation of 3. And now we're using F, which is empty into F, and using and found this value, and F naught we've been using this formula, and found 737. And we are assured that F naught into FC we are taken 6.3. It is taken 6.3 as we've been in the previous calculation. Now step 3, we're using the concrete in bottom and top. So using this formula for getting the area of concrete at bottom is found this year, and concrete is this formula have been found this year. So we can we have been seen that this is the bigger value, that's why we've been taking the bigger value. So this is we can use the, we have provided this value, but we have been found this value. So increase the dimension and redesign. This is the final recommendation. So for each for T section we is using this formula, and we are taking the I bar is here. Okay, I hope there's the these are the index. So I will see the elastic design composite section and math example. So we are going to the this book, and this is the elastic design and composite section. As the discussed previously, composite section is of a pre-stress portion to be combined with another cast in place portion, which is usually formed part all of the top flange and beam. This design composite section is more compliant than other the simple because they are mainly possible combination make up the composite section. Okay, so these are the step is given here. The first step is here, total the elastic design of composite section. We've been seeing the precast portion of stress distribution at transformation is here, and the composite section of stress distribution under working load. Then the stress diagram will be like this. And step 2 as usually is using this formula, and step 3 as usually using this formula, and the final step 4 using this formula. Okay, so let's see an example, then it will be easy. The top flange of composite section is given in slab 4 inch in thickness and 16 inches wide in cast in place, and design the prestressed section in total depth is 63 inches including sub thickness and carrying the working load, and all the data is given here, and allowance stress data is given here, and initial pre-stress is given here, effective stress given here, and all the data is given here. Now we have been seen this is the diagram, example diagram. We have been seen this is the 16 inch flange width, and the flange thickness is 4 inches given, and this is the wire dimension is given here. Okay, so assume the section is make preliminary design for lever arm. We can use this formula and finding F, and after getting friend, and we'll using the F0, and we'll calculating area of concrete which is found in this below. From the preliminary section sketch in trial section we've been found this, and area of concrete we've been found 168, and K top and K bottom we've been found respectively below. Now we've been seen for the composite section the properties are given here. So I section precast portion we've been found this below as a moment of inertia. Moment of inertia is already an M top we've been found this below, and bottom is found this below. Now step 1 the location of CGS using this formula and found this below, and step 2 compared to the above MT and MB, and step 3 and compute the F using this formula and found this below, and F0 is also is here as previously found. So as we've been seen F0 is here, you need to follow this formula, and total you've been found, and which is indicate CGS can be located found in this way, and above the bottom fiber, and new E plus K1 is found this value, and F can be revised which is 114 into this value and found 1460, and F0 is been found 160. Step 2 to keep the bottom fiber within allowed fiber stress using this formula, and keep the allowable stress allowable top fiber within this formula. Okay, so the top fiber is not controlling in this case, and the SE is required to the above of the bottom stress is given here, which is very close to SE of 168 inch square, and furnished by the trial section, and the design considered in satisfactory. Okay, these are the final value of S. Okay, so let's see. These are the index. So let's see ultimate design. This also taken from here. The ultimate design, you can see the only ultimate design for simple section with the blended tendon will be discussed here. Okay, so preliminary design, as we know here, we have been using the this formula for preliminary design, and under compression is here. So example, make the preliminary design for prestressed concrete section is given here, and height of carry total dead load and live load is moment is here. Using steel is ultimate strength is given here, and concrete steel is here. Use the ultimate design and assume the bonded beam. Okay, so we've been seeing here for safety factor 2 steel, we've been used this formula and found this area of steel. Using the load factor 2.4 concrete, using this formula and found the steel here. This is the preliminary section sketch of figure is given, and the provided ultimate area is given 98 inch square, under the compression, so it will be remember. And assume the ultimate moment axis to be 10 inches square below the fiber top, and noted the exact solution of ultimate neutral axis cannot be cannot and need not to obtain the preliminary design, but assume to be 30% of the effective depth of the section. This is the assume, so it will be keep in mind. So the final example is given here, the data is given here, and the final design will give in although all of the preliminary design. This is the final. We can see another example is make the final design. This is the final design will be example 6.8. So what this is the 6.8 as we have been doing the preliminary design. So now we'll do the final design based on the ultimate strength and solution. And the trial error procedure is considered a conventional purpose using the preliminary solution obtained 6.4, and first trial section 6.18 we can use this proceed. Okay, so let's see. So with the ultimate axis we've been found at 10 inches square and found this below. This is the ultimate compressive force location. Okay, 3.4 inch from fiber with the CGS located 3 inches square fiber, and ultimate lever arm we've been found 29.8. Now the area of the steel preliminary decoyed using this formula and found 1.17 inches square. Okay, so you can see which is very near to the preliminary design. We've been found 1.1 inches square, and no further trial is necessary. Design of top flange may be done with example 6.8, and tensile stress should also be checked in the top flange and fiber, since the bottom flange is seldom controlled by the ultimate strength consideration. In ultimate check of elastic stress to web has to be designed in shear, which is considered discontinuous chapter 7. Okay, so these are the final design. So so if we see another section, the I section is another, we can use this formula, but we are escaping here. Now we are seeing the shape of concrete section, which is I, T and box, etc. So let's see the shape of concrete section. They having the studies both elastic and ultimate design. We are now ready to discuss the section of the best shape of the prestressed concrete section under the flexure. So you can see here the hinge, the other section of liquid use prestressed concrete with a symmetrically I section, unsymmetric I section, T section, inverted T section, box section. These are the 5 sections we've been seeing. The shape of the concrete section we've been seeing here: rectangular section, symmetric I section, unsymmetric I section, as the top and bottom are unsymmetric, top and bottom are unsymmetric. T, this is the T section, and inverted T, this is the inverted T, and this is the both T joint, and the box section we've been found in here. Okay, so we can see here Washington State standard beam. We have been seeing here the type of nominal span. If the span is 40 meter of bridge or girder, then we've been used this dimension. The girder span is 60 feet, that will be not meter feet. Then we will be using this, and 80 feet this, and this is the bridge we've been used 100 feet. Then it will be used this. Remember that I have been seen here another which is 38.3 and prestressed girder, which 38.35. That means if we divide it by 3.9, that is the 100. So this is the 100, and the it will be also 100. So dimension is given here. So all the dimension is given here as per Washington State standard beam. Okay, so here is another standard as to PVC prestressed concrete IBDM in a highway bridge. As we can see, this is the type 1, this is the type 2, type 3, and type 4, type 5, and type 6. All the dimension is given as per AS2. And we have been seeing this is the beam type, and area is given, moment of inertia CB, and recommendation span limit we have been seen in feet. The maximum feet we have been from 100 to 104, which is 4. Type 6, this is the type 6. Okay, So another we can see the standard S2 PSI standard concrete box beam for highway bridge. This is the we can see BI 36, BI 30, 38. This is the 36, also 30, 48. So sorry, it will be 48 and 36 also. This is the 48 and 36 and 48, and it will be BY B4, BI3, B2, B1, B1, B2, B3, B4. All the standard is given here. After we've been doing the table of properties, beam section B1 36 to B1 4, and the area, moment of inertia CB, and the recommendation for span length will depend of the standard and straightforward. The maximum is 103 feet. So using this one B14, that means this profile. Okay. So I hope that the shape correction concrete section is now. We'll see the another arrangement of steel. Sorry, now we'll see the design of the standard precast section. So non-composite section may be design of the standard in single trees, double trees, and hollow core section are made using design which is allow the section of the trial from the load cable. So you can see here the composite section. So we can see here the design of composite section system with the standard precast beam. We can see here the composite structural section. So you can see precast beam is here. This is the B maximum. Yes, the effective width of B. So you can see B prime, and F prime is given here. The section of the elastic analysis modifier for different F prime C value. You can see B B slab BEC into B, which is 0.81 B. The design example is given here. The design the composite prestress concrete section. All the data is here, and determine the. I'm just skipping, and if you want, you can using this. Okay, use this calculation found in this value and this value and this value, and using a number of start we have been found 31, which we can use the 32. These are the important how we'll calculate the stand. So let's see. I just need this. Okay, so design composite structural system for the simple supported 90 feet span and beam will be type 3 standard section as you have been seen the previously, and 6 into 6 and composite slab. And design the loads are dead load of the composite section is WG, and additional dead load WD is given, and live load is given, and the nominal of concrete prestress beam is specified this value and this value, and appearance is get design the unshored beam in constructing the following. Yes, a could critical section of mid section, assume the total loss of the prestress is 20% of this section, and all the data is given. And then first of all determine the prestress standard arrangement and full utilize of the prestress beam, and find the maximum space of the beam structural system based on the allowable prestress surface, and check the strength of the ACI code. Okay, let's see the solution. I assume G equal to 5 inches and figure 6.3. So the force F naught is found in this formula, and section properties beam is given here. All the section properties is given, WG, all the these are the given, and E is found here, and fiber top stress in top, F naught initial is found in there, and F bottom is found in there. UCF naught is 409 on keep based on prime C is better. I will calculate the number of stress. This is 906, which is initial, and 28. I will get the 28, which is 0.6% of prime C. These are the 28.9. I will calculate the 28.9. Let's see, 28.9. Okay, 28.9. It is given somehow. 28 is given a prime C. Okay, it is taken from here, the allowable stress, concrete stress, but it will be maybe load 28. So why I'm trying to get this, it will be load, where is F, 28, maybe 28.9 design load W, uh, 20% W load. Okay, it will be check on. I will check. I will calculate number of stress is 31, and check the CGS pattern is here, and all the data we've been found there, and this is we've been 32 we've been found. So we'll using 32 value strength is here, and we can use this also calculation. I'm just keeping the composite section example here. The arrangement of now we'll see the last is arrangement of steel. This is the uh, uh, last portion, Prestressing stage. The arrangement of steel is governed by the basic principle. Okay, what is the principle? In order to obtain the maximum lever arm from initial resistance moment, it must be placed near the tensile edge of the possible. Okay, so you can see the girder moment of insufficient bring to the C within current. This is the C within current, the below current, lower current. This is the stress distribution, this is the compression, this is the tension, and this is the section. And the free stress in two stage keep in C, keep stage K in within current. We will see this is the section in partially stress T1 for M girder moment is only, and the total stress T for girder moment plus MS, and the diagram will be stress diagram will be same. So you can use you can see that this example also I'm just keeping here. In this way you can use this formula. I'm just keeping here. The CC star we can, you can use this formula. We can you can see that this formula. They are the pre-stress steel fans of the reducing section. I hope that these are the in depth. If you have any question, then let me know. I hope that you can understand all these things. Thank you everyone for your questions.